So here we're given the question of arranging these molecules from lowest to highest osmotic pressure. So here at the bottom, I'm just going to label lowest to highest so we can keep track of which direction we're moving in. Now to begin, we're going to start with magnesium oxide. So if we take a look at our osmotic pressure equation, we can see that we have pi equals Van 't Hoff factor times molarity times that ideal gas law constant times temperature. For all of these different molecules, the ideal gas law constant is going to be the same. So since it's the same in all of them, I'm going to cancel it out. It's not going to make a difference in which one has the largest or smallest osmotic pressure because it's the same value in all of them. Same with the temperature. The temperature isn't given in the question, so I'm going to assume that the temperature is the same for all of the molecules. Now, if the temperature is the same for all of the molecules, it's not going to impact which one has the higher or lower value, so I'm going to cross it out as well. Now we're just left with the Van 't Hoff factor and the molarity. Now, starting from the magnesium oxide, and I write out pi equals Van 't Hoff factor times molarity. Van 't Hoff factor represents the amount of stuff. So if we have magnesium oxide and we dissolve it and we get Mg at 2 plus and we get O2 minus. How much stuff do we have? Well, we have one thing and we have another thing. So we have two things. If we have two things, that means our Van 't Hoff factor is going to be equal to 2. I hope that makes sense. Van 't Hoff factor just represents the amount of stuff that we have if it dissolves in our solution. And what's important to remember here is that when we're talking about what's dissolving, we're always talking about the ionic molecules. So over here, we're going to have a Van 't Hoff factor of 2, and now we're going to take a look at our molarity. So our molarity is 0.1. But remember that we had the magnesium 2 plus and we had that oxygen minus. And if it's going to separate into its ions, we're going to have 0.1 of both the oxygen and the magnesium. So we're going 0.1 for the magnesium and 0.1 for the oxygen, which is going to give us 0.02. So the osmotic pressure magnesium oxide is 0.02. Now let's take a look at lithium fluoride. Now lithium fluoride is similar to magnesium oxide because once again, if we dissolve lithium fluoride, we're going to end up with lithium plus and fluoride minus. So we're going to, since it's an ionic compound, it's going to dissociate and we're going to get 0.4 lithium and we're going to get 0.4 fluoride. And how much stuff do we have? Well, we have one thing and we have another thing, so we have two things. So our Van 't Hoff factor is going to be 2. And since we have lithium and fluoride, because it's an ionic compound and it's going to dissociate into its ions and anions and cations, 0.4 times 0.4 is going to give us 1.6. So overall, we're going to get 3.2. So for lithium fluoride, we're going to get 3.2. Now taking a look at our last molecule, we have glucose. Now glucose is not an ionic compound, so it's not going to dissociate into its cations and anions. So however much stuff that we start off with, that's how much stuff we're going to end up with. So our Van 't Hoff factor in this case is going to be 1 because glucose is not an ionic compound and it will not dissociate into cations and anions. Then the molarity, if we only have one of the stuff, it's going to simply remain as 0.6. So glucose is going to have an osmotic pressure of 0.6. Now what I want you guys to make note of over here is that these values of 0.6, 3.2, and 0.02 are not the exact osmotic pressure values because remember, we're ignoring the ideal gas law constant and the temperature, and we're only ignoring it because it's the same for all of these molecules, so it's not going to make a difference in determining which one is higher or lower. But if you want to find out the exact osmotic pressure value, you have to multiply both the ideal gas law constant and the temperature. But regardless of that, we can now label from highest to lowest, and we can state that the magnesium oxide has the smallest osmotic pressure, The glucose of C6H12O6 is going to have the second smallest, and then lithium fluoride has the largest osmotic pressure in this question.